everyone. My name is Kamron. Today I will be presenting our research on the security assessment of in-bicycle network intrusion detection in real life scenarios. And here is an overview of today's presentation: the introduction, background, experimental part, and experimental performance, discussion, and conclusion. And let's start with the introduction to our research. And first of all, let's discuss about the issue and an electronic control unit and monitors and analyzes electronic signals to identify and diagnose issues in the bicycle. It controls all devices, including the engine, transmission, and other critical components. The in-bicycle network, IVN, initially employed UART for communication between modules in one-to-one manner, which is an unsynchronized serial communication method. This evolved to the CAN, control area network, for efficient and noise-resistant communication, capable of transmitting 8 bytes and data at maximum speed of 1 megabit second, and CAN remains the predominant communication protocol in modern bicycles. And let's discuss about the CAN, designed for enabling communication between control devices in the bicycle, including the host computer. CAN is utilized the communication process between SUs within the bicycle internal network. It's the most used standard communication protocol in bicycle internal networks. CAN is classified based on identifier lengths. Standard CAN and standard CAN used 11-bit identifiers, while extended CAN used 29-bit identifiers and support both standard and extended CAN forms. And in this picture, we can see the difference between the standard and extended CAN formats. And standard CAN features an ID length of 11 bits and data length of 8 bytes and maximum speed of 250 kilobits. In contrast, extended CAN features an ID length of 29 bits and data length of 8 bytes and maximum speed of 1 megabit second. Both versions ensure reliable communication within in-bicycle network. And let's move on the background of our study. First of all, it's necessary to discuss the attack targeted attacks targeted at the CAN system, which were recorded and as a dataset for subsequent use in training our model. The first attack was a DOS, denial of service. Attack is a hostile action that disrupts normal system functioning by overwhelming the network with excessive message. This leads to system overload, and the injection technique is a DOS attack involved flooding the CAN bus with message cause this overload. Especially messages are injected at very short intervals, typically between 0.3 to 0.5 milliseconds. This rapid succession ensures the system is continuously bombarded, preventing regular traffic from the beginning process. For executing this attack, a data containing the CAN ID was 000, and the ID is repeatedly sent to float the bus and achieve the desired disruption. In summary, a DOS attack CAN bus involves strategic flooding of the network with message at very short intervals and leading to the system overload. And let's discuss about the fuzz attack, a method designed to uncover system weakness and potential entry points. A fuzz attack injection randoms and inconsistency into the CAN bus to identify vulnerabilities within the system. The injection technique in fuzz attack involves sending random CAN IDs and data at intervals like those. These randoms are intended to uncover weak spots and potential entry points for further exploitations. A data set incorporating random can IDs or irregular data is used to execute this attack. In summary, a fast attack on the canvas involved injecting random and inconsistent data a short interval to discover vulnerabilities within the system. And now let's discuss replay attack, which involve the interception and resending of genius communications. A replay attack is a method where valid communications are intercepted, recorded, and then retransmitted to disrupt normal operation or gain unauthorized access. The injection technique is a replay attack involve executing the retransmission as intervals with like similarity with DOS and FAS attacks. This rapid retransmission mimics legitimate traffic but can lead to confusion or unauthorized action within the system. A data set that includes recorded message with their original IDs is used to carry out these attacks. By replaying those genuine communication, attackers can effectively bypass security measures and manipulate the system. In the summary, a replay attack involves the interception, recording, and retransmission of valid communication at short intervals and disrupt the normal operation or gain unauthorized access. For intrusion detection system, we built LSTM model. LSTM model is designed to handle long-term dependencies in sequential data. It features memory cells and three keys components: input gates, forget gates, and output gates. And these gates control information flow, allowing LSTM to retain important data and discard irrelevant information, thus solving the gradient vanishing problem found in traditional RNN models. And LSTM is ideal for capturing complex temporal patterns in sequential data and and making it useful for applications such as language modeling and time series predictions. And let's move on the experimental method for our study. And problem statement was in our research, we conducted an analysis of weakness of certain methods under real-life conditions. Through a series of experiments, we identified vulnerabilities in methods that have previously been recommended as the most effective models for intrusion detection system and optimal approaches for training those models. The distinct model types were created in Korean study and trained used various methods. Feature extraction, we choose the three types of feature extraction. The first one is CAN-ID, second one payload, and the last one is full data. And the research was based on testing those model on CAN system under an identical assault scenario where they effectively identify abnormalities. And let's discuss about the structure of our experimental part. In the experimental methodology, we will initially select the required dataset and consolidate them into the single dataset, which includes both attack-free data and attack data with labeling. Subsequently, the model will be trained using three feature extraction methods like CAN-ID, payload, and full data. After training the model, we will be tested against similar attack scenarios to evaluate its performance. Following this attack scenario will be altered either randomly or according of specific criteria, and the models will then be tested using the improvised dataset to assess their robustness and adaptability to the new attack patterns. In this page, we can see our view of dataset, and we choose three, as I told, three types of feature extraction. The first one, CAN-ID, payload, and in the end, we choose the columns, like the feature extraction. And as you know, the pre-processing data playing a crucial role before training the model. We employed two methods, label encoder at first, and after that mean normalization. Given that we had used the label encoder, is a tool that improvised stability and model training efficient by converting the categorical data into the format that machine learning models can process directly. This numerical representation ensures that the algorithm interpret the data correctly and leverage the information contained within the categorical features. And the second one is the mean normalization. For pre-processing, we use mean normalization, and its data pre-processing technique uses the scale and center the values of the data sets. And it involves subtracting the mean average of the data from each data point and then dividing the results by the standard deviation or the range of the data. This process does not change the shape of the data distributions, but ensures that the data centered around zero. Mean normalization is the particularly useful when working with the features that have different scales, and as it brings all features to similar scale, making it easier to compare and analyze them. And let's discuss about the experimental performance. Firstly, we developed three models, each utilized different feature extraction method. CAN-ID, the first of one was CAN-ID model, which focused on control area network identifiers. The payload model, and which analyzed the payload within the CAN message, and full data model, which used the entire dataset without specific feature extraction. This model we tested under intentional attack scenario to ensure a fair comparison. The test results we proposing as three model height efficient in the detecting and countering attacks. This initial success demonstrates the potential of three models controlled environment. However, in the real work, it's impossible to guarantee that all attack scenarios will be identical. Models trained on specific scenarios may not provide the comprehensive security. For instance, consider the key assault, where the most critical CAN-ID is 0018, and many research select those attack scenarios by sending priority message with the CAN-ID 000 through the CAN system. Our analysis showed that there are actually 70 possible DOS attack variants, ranging from the CAN-ID 00 to the CAN-ID 0070. And this diversity of potential attack poses a significant challenge for model trained a single scenario. And our research demonstrates that model with high accuracy on specific scenarios cannot effectively detect other types of attack. For example, a model trained on DOS attack with labeled CAN-ID the 000 will not be able to recognize an attack within the CAN ID 0015. And this limitation underscores the need for models to be trained on broader range of the scenario and hence their detection capabilities. And for testing our models, we improvise the dataset. In those attack, in original version, DOS attack was the 000. For the improvised version, 4 digital value were generated, considering that real CAN IDs in Soul card typical short with the 0018. The selected DOS CAN ID from for the attack were 0015, 008, 0017, and 002, and 003. For payload modification, the values in payload 1, 2, and 3 and 4 columns were set of the FF. For rows, where the CAN ID matched any of the selection attack IDs like the DOS. And fuzzing attack modification, initially CAN IDs was 2A0 and 081 and 260 and 1F1 were chosen for the fuzzing attack. The improvised version and those CAN ID were changed to the 1A0 and 1080 and 250 and 009. For payload modification, the values in payload columns were set 00. For rows where CAN ID was 017. Additionally, for rows with the CAN ID 165 and payload 1, value of FF, and for rows with the CAN ID 370 and 440. And the values in payload 5 column were set to the FF. And this is our experimental results. During the training phase, our model achieved the 99 accuracy rate when tested an original data set, which was trained the similar scenarios of attacks. And however, when we test on improvised dataset, the accuracy rate dropped to the 79. And in subsequent experimental involving payload data, the model achieved 98 accuracy rate on the original test data. Unfortunately, when we evaluated on improvised data, the accuracy decreased to the 81. And in the third experimental model, trained using all columns achieved 99 on the test data, but their accuracy dropped to the 19 when tested with improvised data. In the picture, we can see the results, difference original and improvised data set results. And let's discuss about the results and our research findings. And those results indicated that models trained on specific columns and the model proposed earlier are not considered effective. And to enhance the effectiveness of IDS, considering time gap features between two packets with CAN ID sequence is recommended. This approach offers several advantages. Utilizing the entire dataset could lead to the more complex model that is the computationally less efficient. Focusing on time gap features allows for the simplified model while still capturing critical information. Also, to make the model work is in different situations and help the data become more general, it's a good idea to investigate approaches, like converting the data into the frequency domain. Those techniques can enhance the IDS ability to detect intrusion under different scenarios and conditions, making it more versatile and practical. And in the end, let's discuss about the conclusion. In conclusion, our experiment revealed limitation in the training methods used for CAN-based IDS. By comparing models trained on CAN-ID payload and full dataset parameters, we observed significant performance differences, and model trained of specific feature performed well on controlled test data, but poorly on improvised dataset, highlighting their limitation in real-world scenarios. And this underscores the need for more robust, adaptable IDS system. Future research should prioritize finding appropriate features and improvising data generability to better protect in-bicycle network against and evolving attack scenarios. And thank you all for your time and attention. Do you have any question?